So in this problem, we are asked first to find the stopping distance of a car given a certain coefficient of static friction with the ground. So I'm just going to draw an isolation diagram for the car. We have the force of gravity, mg pulling it downwards, the normal force pushing it back up, and the force of static friction pushing it to the left. It's static friction because the wheels are rolling without slipping. So this tells us, using our sum of the forces, that if this is the positive x direction and this is the positive y direction, the sum of the forces is going to be minus the force of friction, because mg and the normal force cancel out, which is just minus mu sub s times n equals minus mu sub s m with g. And this is going to be equal to ma, as we know, because it's the sum of the forces. This tells us that a is equal to minus mu sub s times g. Now we're going to have to do a little bit of calculus. This is equal to dv dt, which tells us that we can take the integral dt of these two things. This is going to be from 0 to t. This is going to be from v naught to v at time t. This is going to be a function, and this is going to tell us, as a function of time, what velocity is going to be at any given point. So this tells us v of t minus v naught is equal to minus mu sub s g t, which ultimately tells us v of t is equal to v naught minus mu sub s gt. Now we can use this again, and this is just dx dt, because that's exactly what v of t is. And we can integrate that dt. Remember that v naught is a constant, not a function, which means that when we integrate it, it's just going to be multiplied by a constant t. So this is going to be from 0 to t and 0 to x, setting its initial position to be 0 and x to be the distance from there at any given point. This tells us x of t is equal to v naught times t minus mu sub s times g times t squared over 2. So now, in order to use this, we need to find the stopping time, big T, because that's going to tell us what distance we've gone after that time. So for that, we're actually going to use this. So v at time big T is equal to 0, which tells us that v naught is equal to mu sub s times g times big T, and big T is equal to v naught over mu sub s times g. And that makes sense, right? Because if it starts with v naught and it's decelerating at a rate mu sub s times g, it's going to take the ratio of that in time before it comes to a halt. So now we can plug this in to find the stopping distance d. d is equal to x of big T is equal to v naught times big T minus mu sub s times g times big T squared over 2, which is v naught times v naught over mu sub s g minus mu sub s g times v naught over mu sub s g squared over 2, which is v naught squared over mu sub s g minus v naught squared over 2 mu sub s g, which is just v naught squared over 2 mu sub s times g. So this is d, our final stopping distance. So in the second case, instead of just stopping, our driver is, in order to avoid the obstacle, I believe there's a wall that this driver is trying to avoid. So in the first case, he just slammed on the brakes, attempting to stop before hitting the wall. In this case, he's going to swerve circularly to try to avoid it. So he's going to swerve with some radius r, and if the obstacle is at this distance r, then r defines the minimum safe distance. So if the driver is less than a distance r away from the wall, then he's going to crash into the wall because he's not going to be able to turn fast enough. So in this case, we get, again, that the sum of the forces equals ma is equal to minus mu sub s times mg. And so we get a is equal to minus mu sub sg again. But in this case, a is also going to be equal to minus v squared over r. Because remember, centripetal acceleration is negative because it points radially inward, and it has the value, or the magnitude, of v squared over r. So this tells us that r times mu sub sg is equal to v squared, canceling out the negatives, and r is equal to v squared over mu sub s times g. And now, comparing this to the distance that we got in the previous calculation, this tells us r is equal to 2 times d. So all that means is that stopping is going to be able to get you out of a danger that is twice as close to you. So if you notice that for whatever reason you're speeding towards a wall, slamming on your brakes is more likely to prevent you from hitting it because it has a minimum safe distance that is half as far.